Today we're going to be going over the Chapter 9 review questions, and so these are all found at the end of the chapter. I do have a bit of a glare going on, so hopefully it's not too much of a problem. So for the first question, I'm going to skip because those are just definitions, so it's matching the term with the definition, and I'm not going to spend time on that. But I would recommend you take the time to look those up and learn them. But number 2, we're going to start with that bronze is a homogeneous mixture of copper with mostly copper with small amounts of another metals mixed in it. Usually they mix in tin into bronze and some different other metals a lot of times in the compound. And so the question asks you, what is the solute and what is the solvent? And solvent is the copper, because we have almost all copper and we're adding to the copper a little bit of tin. So since we're basically mostly copper, copper is our solvent and our solute is tin. The question then goes on to ask a part that I did not write down, where it asks you, it says, what do we call a solution that's made from a metal and other solids? And so if you remember from the readings, these mixtures of metals are called alloys. And we mix metals to give them different properties like strength. Question number 3, I didn't write down the whole question, I'll just read it to you. But the question asks, which will conduct electricity? A solution of water and this compound, ammonium sulfide, or this compound. And so it wants to know which one's going to conduct electricity. Well, you should remember that ionic compounds conduct electricity and covalent or molecular compounds do not. And so when I'm looking for an ionic compound, I am looking for a compound that has a metal in it or ions or polyatomic ions. So if I look at my compounds here, this one has a polyatomic ion in it and sulfur. So even though it has only non-metals, it does have this ion. And this one is just a carbohydrate and it is all covalently bonded, so it does not act as ionic. So the one that would conduct electricity in a solution is the first one. The 4th question says, if you looked at a solution of potassium phosphate and you see all the molecules and ions, what specific particles would you see? So the first thing is basically we have a liquid and it's aqueous, so we're going to be dissolving powder in it. And so what does this do when it gets into solution? So I'm going to ask myself first, is this an ionic or is it covalent? Because that's going to tell me if it breaks apart or if it stays as one whole compound. And I know that potassium is a metal and this is my polyatomic ion that should be remembered. And so since this is an ionic compound, it's going to break apart and I'm going to have some potassium ions in solution, and then I'm going to have some phosphate ions in solution. And I'm also going to have some water. The question then goes on to ask what is going to make up most of the solution and what is going to make up the least in the solution. Well, the most thing I have in this solution is water, right? And the least is going to be phosphate. Because if you look at your compound, you have 3 times as many potassiums as you have phosphates floating around. So this one's the most, this is the least. So for number 5, I'm not going to write it and I'm really not going to try to draw it. There is in your text a picture of a drawing and there is in your text a picture of a drawing and it has this drawing here. And it's asking you what is wrong with how the molecules are, like what's wrong with the picture. And so for this picture, the water molecules are not oriented correctly. The red dots on the water, so that 2 white dots and the red dots are actually your water molecules. And so water is H2O, so it's 2 hydrogens and 1 oxygen. So the white are your hydrogens and the red is your oxygen. Well, oxygen has a charge of -2, and so it's going to be drawn to the positive end of the solution, or of the, I'm not even sure what this is supposed to be. Red should be going towards the positive parts. In some cases, you can kind of see like it has the positive hydrogens near it. Number 6, we have an aqueous solution that contains in it 3 sulfate ions for every 2 aluminum ions. And so it wants to know what was the solute that was added to the solution. So even though once it's in the solution, the ions are separated into sulfate and aluminum, if it was the solute when it was added, they were in an ionic bond. And so since we have 2 aluminum, I'm going to do aluminum first because it's the cation or the metal, and 3 sulfates. And if you'll remember, when you have multiple polyatomic ions, you have to put them in parentheses. And I could double check this by checking to see that the charge is balanced out. So aluminum has a charge of 3, and this has a charge of 2. And so the charges, if I did the crisscross method, they check out. So that's aluminum sulfate. Number 7 says that I am going to be making a solution by dissolving a solid of silver nitrate into a solvent of water. And it wants to know, what can I do to change the temperature of my solution to increase its solubility? So how can I make it so that I can put more of this solid into the water? And if you'll remember our solubility rules, when you have a solid solute, that when you increase the temperature of the solvent, it can dissolve more. So just like if you warm up the water, it could dissolve more. So what would I do with the temperature to increase the solubility? I would just increase the temperature. Number 8, you're trying to dissolve as much of a gas into water as you can possibly dissolve. How should you adjust the temperature and the pressure? Well, remember, with gases, our solubility rules are almost the opposite of what they are when you're talking about a solid in the previous problem. So with a gas, we talk about how a liquid can hold a gas better if the liquid is colder. So I would decrease the temperature. And then as far as pressure goes, if you think about a soda or a Coke, when you open it up and there's no pressure holding the gas in, the gas leaves. So if I want to keep the gas into the solution, I'm going to put pressure, which is how pressure into the can, so that way when you open the can, you hear that nice little hiss noise, but that is also holding the gas into the Coke. Number 9 is actually referring to the second part of experiment 9.1, if you did that one in the text. But it says a solution of a solid solute is saturated. If the temperature is lowered, what will happen? So in the lab, you take a solution of water, you take water and you dissolve as much solid like salt as you can get into it. In the lab, you heat up a sample of water and you dissolve as much salt as you can get into it, and you make a saturated or supersaturated solution. Then you take that sample and you actually put it in a test tube, and then you put that test tube in ice water. And what you will see happen is, as your salt water cools, you will see some of the salt collect in the bottom of the test tube. And when that happens, when you see a solid falling out of a solution, we call that a precipitate. And so what really is happening is you would see a precipitate form, or you would see some of the solid come out of the solution. Because as you cool it down, you're lowering its solubility and it can't hold all that salt anymore. The molecules get closer together and there's not enough space for the salt to fit in between them. Number 10 gives us an equation. It just says a student performed this following reaction by mixing magnesium chloride with potassium hydroxide. And then it asks, did a precipitate form? Did a precipitate form? And if so, what was the precipitate? So to answer this, we need to know, what is a precipitate? Well, a precipitate is when you see a solid, we say falling out of the solution, just really basically collecting on the bottom of the vessel. And so I am going to pay attention to phase symbols for this. And so phase symbols are these: AQ, which means aqueous. So we have we have a solution in water, we have another solution in water, and we're produced potassium chloride in water, and then magnesium hydroxide, and its phase symbol is an S, so it is a solid. So I can know that magnesium hydroxide is my precipitate. So yes, this does form a precipitate. I know I frequently will drop the phase symbols as I write some of these equations, but when we're dealing with this chapter and in solutions and things like that, it is important to keep them in these equations. Question number 11 is a question where you are basically taking a word problem and you're pulling it out and making the chemical equation or the reaction. These seem to really intimidate people, but if you just take it one step at a time, you can work through it. Make sure that either you know your polyatomic ions before you tackle this, or you have like your little cheat sheet. My students have a card that they've written them down on that you're using as you work through this problem. So the first part is just information they're telling you that you're not going to use at first, which is always a little tricky. But they're saying calcium carbonate is insoluble in water. So we're just going to use that knowledge after we write the equation. But where they tell me to start writing the equation is it says, I have a solution of calcium nitrate and water. So I'm actually not going to use water as a reactant for this. I'm going to use the phase symbol aqueous to show that it is calcium nitrate mixed into water. So I'm going to write calcium nitrate and calcium is in the second group 2, so it has a charge of 2+, and if you have your sheet of polyatomic ions, you're going to be showing that nitrate is a 1. And so to balance out the charges, we have to have 2 nitrates. Then I'm going to say it's in an aqueous solution because it tells me that it's in water. And then I'm mixing it with potassium carbonate and water. So yet once again, potassium carbonate is going to be an aqueous solution. And the charge on carbonate is a 2-, and the charge on potassium, because it's in group 1A, is a 1. So it's going to take 2 potassiums to make this compound. Now, I have to figure out what is going on. And so actually, if you'll remember from your reading, these are what we call double displacement reactions, where essentially the metals swap or they trade partners. So I'm going to trade out with nitrate and put nitrate no longer with calcium, but I'm going to put it with the metal here, which is potassium. And charge on nitrate is 1, charge on potassium is 1, and so I do not have to mess with my subscripts for that. And so for the next one, where I'm going to take carbonate, and I'm not going to have it with potassium, I'm going to put it with calcium. So I'm going to have calcium carbonate. And calcium is also calcium is a 2 charge, and carbonate is a 2 charge, so I do not have to change my subscripts on that. And so what basically I need to know here is calcium carbonate is insoluble in water, and so that lets me know that that's that precipitate. So this guy is a solid. It fell out of the solution, and all the water is still here. So in this equation, it is important to remember your phase symbols. And so unfortunately, we're not finished with this because it is not balanced. So if I look at this equation, I have 2 potassiums, and I only have 1 here. So I'm going to put a 2 here to balance that. And now I have 2 nitrates and 2 nitrates. I also have 1 calcium and 1 calcium and 1 carbonate and 1 carbonate. So all I have to do to balance it is put the 2 in front of potassium nitrate. So when we start question number 12, we are actually entering concentrations. And so for this one, it tells me I have a solution, and it's being made by dissolving 100 grams of lithium sulfate in enough water to make, I have that wrong. In enough water to make a 325 milliliters of solution. What is the concentration in moles per liter? And I hope you know at this point, or you remember that moles per liter is molarity. And so really have 2 conversions before I can get to moles per liter. First, I have to know moles, which I don't know because they gave it to me in grams, but we have had so much practice at this point going from grams to moles. So you're going to add up whatever the atomic mass of Li to SO4 I'm going to go back to good old basic stoichiometry here, and I'm using my molar mass for my periodic table where I've added up lithium and sulfate, and I know that those have molar mass of 109.94, and so 100 grams divided by this, grams cancel out, and I'm left with my moles of lithium sulfate. Now I also need to know liters, but we can do that really quickly if you remember with King Herod dying. We're just going to move that 3 times, your decimal 3 times. Because it's in milliliters, so I go 1, 2, 3. And that is the problem for molarity of this. And so the end result, I'm keeping with is 2.799. And yes, I have 4 significant figures throughout that problem. Number 13 says, I want to make a 225 milliliter solution of 4.5 molar solution. And so this is like NaOH. We've used this some in lab. It's lye, it's very caustic, so we always have to wear goggles when we're dealing with this. But the question wants to know, how many grams of NaOH do I have to start with so that I end up with 225 milliliters of a 4.5 molar solution? And so I actually cannot use molarity to solve for grams, but I can use molarity to solve for moles. And so why wouldn't I use, this does have grams in it for molality, but it's grams of the solvent, not grams of the solute. So I'm going to be using molarity, and I know molarity, and I know my liters, 0, I'm going to convert it to liters. They always have to give you that extra step, right? And I'm going to solve for moles. And this is moles of NaOH. So I'm just going to multiply these 2 numbers together, and I get 1 mole. Now that I know my moles of NaOH, I can then go back and use my molar mass to calculate what they're asking for, which is grams of NaOH. I'm going to put grams on top, moles on the bottom, so it cancels out. My molar mass of NaOH is 40. And so 1 times 40 equals 40. 40 grams of sodium hydroxide. So basically what I'm doing is, since my question's asking for grams, I can't straight figure out grams. I can figure out moles first of NaOH that I have to use, and then I can actually calculate to the grams. And so now I know that if I took 40 grams of this and I added it to 220 to make 225 milliliters of solution, this is the molarity of the solution that you would have. Number 14 is one of those word problems where we're going to have a long process of steps, and so it's going to get a little confusing. So try really hard to keep your work orderly, make it make sense and flow so you don't get lost in just what we're doing in the problem. All right, so it tells me a chemist wants to make cobalt hydroxide, and they give me this very long formula on how to do that, and then they give me a bunch of data. So it tells me I'm going to be using 167.4 milliliters of a molar solution of NaOH. That's this one right here. So I'm just going to add that right above it. And I have excess of that product, of that reactant. And so I'm looking for how many grams of this are being formed. And so this actually has quite a few steps. Let's look backwards. If I'm trying to figure out how many grams are formed, the first probably going to calculate are how many moles are formed. Well, in order to know how many moles of this are formed, I need to know how many moles I start with. Well, I'm not going to know how many moles I start with of cobalt chloride because it's in excess. I have lots of it, and it's not a precise number. But I can calculate moles of sodium hydroxide. So I'm going to calculate moles of sodium hydroxide, then I'm going to go to moles of this product, and then I'm going to do grams of this product. So let's first calculate moles of sodium hydroxide. So I'm going to use that using molarity. They give me the molarity. And it's moles over liter, but I don't know moles. I do know liters. Of course, it's given to me in milliliters, so you can do that quick conversion. And so if I multiply these two numbers, I get, sure I'm writing it right, 0.233 moles of NaOH. So if I know how many moles of NaOH I have, I can go to moles of the product, of the cobalt hydroxide. I go from moles to moles using the coefficients in front of the balanced chemical equation. And they already gave you this equation balanced, so I'm going to be using this data. So I want NaOH to cancel out, so I'm going to put it on the bottom. It's moles. And I'm going to moles of this. And so 1 mole reacts to 2. Moles of NaOH cancel out. In my calculator, I'm going to put 0.233 divided by 2. And I get 0.117. So I was able to calculate how many moles of the cobalt hydroxide, but it doesn't ask for moles, it asks for grams. So they give us one more step. Feel like I'm getting messier handwriting. So once I know my moles of the product, I'm going to use my molar mass to calculate to grams. And so from my periodic table, I can add up that my molar mass is 92.95. So this is the 2 hydroxides and the cobalt. And so once I do that multiplication, I get 10.9 grams of the product is produced. So 10.9. So just in case you got lost, I took the information I knew about the concentration here of sodium hydroxide and I converted it to moles of sodium hydroxide. And then I was able to use my equation, my balanced chemical equation coefficients, to go from moles of NaOH to moles of the product. And then I could take moles of this and calculate it to grams, which is what the question was asking. Okay. Question number 15. I didn't write the whole question down, but I did write down the equation. They give us the balanced chemical equation, and they tell us that we're basically doing this reaction, and we're wanting to make 150 grams of this barium carbonate. And it also gives us some information about the products. So it tells me that we have excess of this, and it wants to know the volume, just be a question mark, of barium nitrate. And so I'm kind of working backwards. I'm going from barium carbonate all the way back to barium nitrate. And so, like we talked about in past problems, if you're kind of lost and you maybe not know what to do on these long ones, you're going to convert to moles. So let's start with the 150 grams. So if I start with 150 grams of barium carbonate, I react it or multiply it by the molar mass that I calculated from adding up all the atomic mass units from your periodic table. You get 197.34 grams per mole. So grams cancels out and we're left with 0.7601 moles of barium carbonate. Now the question is actually asking not something to do with barium carbonate, but it's asking me something to do with barium nitrate. And so to go from barium carbonate to barium nitrate, I'm going to use the coefficients of my balanced chemical equation. And very fortunately in this case, there's a 1. It's not written there, but it's understood. And there's a 1 here. It's not written there, but it's understood. And so they react in a 1-to-1 ratio. So if I have this many moles of barium carbonate, it's also the number of moles I have of the reactant. So the other bit of information that they give you in the problem that I didn't yet write down is they tell me the molarity of a solution, of this solution, and it is 2.56. And since I'm trying to find liters, if I know that molarity is moles over liters, I know my molarity is 2.56. I know my moles is 0.7601, and I don't know my liters, but I can solve for it. So you would say, I would multiply liters over here, and then just divide both sides by 2.56. And so your liters would equal 0.7601 divided by 2.56 equals 0.297. That equals 0.297 liters. So just a recap of what we did is we knew the products and we were trying to go to the reactants. And so I had to go from grams to moles. Then I used my balanced chemical equation to go from moles of the reactant, of the products, to moles of the reactant. And then from this moles, I was able to use the molarity and calculate the amount of liters. For number 16, the question says, of the 2 concentration units we've used in this chapter, molarity and molality, which one is a ratio of the amount of solute to the amount of solvent? And so if we look here, we have solute to solution is molarity, and molality is the amount of solute to the solution. So the answer for number 16 is molality. Number 17 says I'm making a solution by mixing 67.8 grams of potassium chloride with 450 grams of water. And it wants to know what's the molality of the solution. So find molality, I need the moles of the solute over the kilograms of the solvent. Well, I can easily figure out the kilograms of the solvent, but I have to calculate the moles of the solute from this grams. So I'm going to start with 67.8 grams. I feel like we have done these grams to moles, moles to grams calculations so many times over the last few weeks. So 1 mole, I add up a potassium and I add up a chlorine, 74.55 grams. And so grams cancel out and I am left with 0.9 moles. So now I'm going to take that and I'm going to put it into my molality equation. So my little m is going to equal 0.909 moles. And remember, it's got to be in kilograms over solvent. So I'm just going to take my decimal and I'm going to move it 3 times to the left because there are 1,000 grams in a kilogram. I'm just going to do the basic division there, and you should get .02 as a molality. This is your concentration of the solution that we have made. Number 18 is another molality solution, except this time they give me the molality and I'm solving for a part of it. So a chemist makes a 2.34 molality solution by mixing 23.1 grams of magnesium chloride with water. How many kilograms of water are we using? So for molality, remember we need moles of solute over kilograms of solvent. So I know my molality, I know this part of the equation, and I know kind of in grams, the moles of the solute, and I'm trying to figure out the water. But the first thing I do is I have to get this that they gave me in grams into moles. So moles to grams again. So if I'm going moles to grams, I've got 23.1 grams of magnesium chloride. From adding up the masses on the periodic table, there's 95.21 grams for every mole of magnesium chloride. Grams cancels out, so I put into my calculator 23.1 divided by 95.21, and I get 0.243 moles of magnesium chloride. So now I'm going to solve it for using the molality equation. So I'm going to say molality, which they tell me 2.34. And I know my moles of my solute is 0.243. And I do not know the kilograms of water. So this is what I'm solving for. So I'm going to multiply both sides by kilograms so that this cancels out. Then I'm going to divide this side by 2.34. So I have kilograms. Should use an eraser, not my fingers, huh? So kilograms equals 0.243 divided by 2.34. Those numbers feel really similar to each other. And I'm going to get 0.104, and this is the kilograms of water that they're asking you for. Number 19, we're going to be using those colligative properties of boiling point elevation and freezing point depression. Now, if you'll remember from the formula, I don't have them written on the board now, but maybe you have it in front of you. There is a part of the formula that is an I, and that is the number of particles. So people like to say ions, but it's not always ions. The number of particles that the compound splits apart when it gets into solution. And so if a compound splits into more particles, they will actually lower the freezing point more or raise the freezing point more. So the question for number 19 says we have solutions of all of these made in water. So we have all these solutes dissolved in water. And the molalities are the same. So in the formula for boiling point elevation or freezing point, the molality of it is all going to be the same. And so it wants to know which one's going to have the lowest freezing point. So all of these are in water, which would have had a freezing point of 0 degrees Celsius. And so we're really looking for which one is going to lower the freezing point the most. And so the variable that is going to depend upon is on the I, or the number of particles. So we're going to figure that out. So magnesium nitrate is an ionic compound because magnesium is a metal. And so it breaks up into one magnesium and into two nitrates. Remember, a polyatomic ion stays the same. So it forms 3. So its I would be 3. For calcium chloride, this is also a metal, so it still breaks apart. So we have 1 calcium and 2 chlorines. So its I is also a 3. All my markers are done. Sodium chloride, we have a metal and a non-metal, so it's ionic, but it's only 2 parts. So 1, 2. For this one, it's actually no metal, it's all non-metal, so it's a covalent compound, so it stays the same in the solution. It doesn't come apart, so it's a 1. All right, this is not a metal, but it is a polyatomic ion, so they do split into the ions. We have 2 ammonium ions and 1 carbonate ion, giving us an I of 3. And then aluminum chloride actually has 1 aluminum, and it splits apart because it's a metal, and 3 chlorine ions, so that is a total of 4. So the salt or the compound that would lower the freezing point of the water the most is the one that has the highest I value, and that is aluminum chloride. And that's why when you have salt that you put on your ground, like when it's freezing outside, there's actually some salts that you would use that, but it has an I of 3, which is bigger than table salt, which is just an I of 2, so it lowers the freezing point more. So this one has the lowest freezing point, and this one would have the highest. So number 20 is a freezing point problem. So we're going to use our freezing point and boiling point equations. If you'll remember, the difference is for freezing point, the constant has a subscript of F and I is negative because the temperature will be going down. And for boiling point, we have a constant with a subscript of B, and I is positive because the temperature will be going up. All right, so for this question, it asked us what is the freezing, whoops, I left out point. So let's just, what is the freezing point? I don't want to rewrite it all. Of a solution made by mixing 32 grams of NaCl, table salt, with 250 grams of water. And then it gives us the K, our constant. And so for this, I'm just going to take the information I have and start plugging it in and seeing what I need. So delta T is what I'm looking for. So I do not know it. For I know I can figure out I with table salt. Sodium's a metal, it's an ionic compound, and so it's going to break apart into its ions, which is sodium and chlorine, so I is a 2. And then I know my constant. And the next thing I need is molality, and I do not have molality. So I have to calculate molality. So if you'll remember for molality, I need the moles of the solute over the kilograms of the solvent. And they actually give me the solvent, the water, but they do not give me the moles. They actually give you grams. So once again, we get to calculate. We're going to go from 32.0 grams of salt So when I take my 32 grams of NaCl, multiply it by my molar mass for my periodic table, which is 58.44 grams. Grams, I don't multiply it, I divide it by it, but grams cancel out, and I'm left with 0.548 moles. I know I'm going through that step really fast, but we have done that step so many times. So I'm trying to figure out the molality. So I need my moles divided by kilograms of solvent, and I have 250 grams of water, and so I'm gonna convert that into kilograms, and so it's 0.250 kilograms. So the molality of this ends up being 2.19. So my little m ends up being 2.19. So what I'm going to do is I'm going to take this and put it up here. So you're going to just multiply, maybe easier if I put an X there instead of a dot, 2 times 1.86 times 2.19, and you get negative 8.15 degrees Celsius. Now, the question doesn't ask for the delta T. The delta T is the difference in temperature. And so for this one, though, it's a little bit easy to figure out because water normally freezes at 0 degrees Celsius. if I'm going to have this be taken away, like lowers the freezing point, instead of freezing at 0 degrees Celsius, it would freeze at negative 8.15. And so even though this is the delta T, it's also the new freezing point. Number 21, same set of problems. A solution made from water and N2H4 has a freezing point of negative 1.5 degrees Celsius. It wants to know what is the molality of my solution, and it gives me the constant. So I'm just going to start with my freezing point equation and see what I can put in and what I need to figure out. So I know it has a freezing point of negative 1.5, and it says it's from water. Well, if water starts at 0 and it goes to negative 1.5, I know my delta T is negative 1.5. And I say negative because it's gone down. So it's negative I into H4. Neither one of these are metals. They're both non-metals. So this is a covalent compound, not an ionic compound. So it does not break apart in solution. So I is just negative 1. I'm going to multiply it by 1.8, getting messy, 1.86, and then M is what I'm trying to solve for. If I work this through algebraically, I get 0.81 molality. And that's all there is to this problem. I believe the biggest step for people that get confused on this one is determining that I is 1, because this is not an ionic compound. So number 22 asks us what's the boiling point of solution from question number 20. And so question number 20 was the solution where we had salt. So we're just going to work through the boiling point equation and see what we have and use our data from the previous question. So I don't know delta T. I'm looking for the boiling point. So that's kind of what I'm looking for. For question number 20, the solute is NaCl. It's an ionic compound and it splits into 2. So I is 2. I'm going to multiply it by my constant, and then I'm going to multiply it by the molality, and I calculated that in that question, and I calculated it to be 2.19. Delta T equals 2.24 degrees Celsius. But it wants to know the boiling point. So the boiling point of water is actually 100 degrees Celsius, and I'm going to be raising the boiling point. So I'm raising it up. So it's like 100 plus 2.24, and I get 802.24 degrees Celsius is the new boiling point for the water. On our last review question for chapter 9. And so it's a little bit different than the other problems, but it says the boiling point of ethanol is 78.37 degrees Celsius. And if the boiling point of a solution of strontium chloride and ethanol is 80.56 degrees Celsius, what is the molality? And so the reason this one is very different from some of the others is that it doesn't use water. We're using ethanol as the solvent. So we have a solution of ethanol and we put into it strontium chloride. And so we want to calculate the molality. So let's just take our equation and see what we have. So if I want to figure out delta T, so the first part is delta T, which is the temperature. I can actually calculate that. I can take 80.56 and subtract 78.37. So if you take 85.56 and you subtract 78.37, you get 2.19 degrees Celsius. So that's your delta T is 2.19 degrees Celsius. And for I, for strontium chloride, strontium is a metal, so it's an ionic compound. So it splits into 1 strontium and 2 chlorines. So I is a 3. And we know Kb. And we're looking for the molality. So if I just solve this through, this would equal 2.19 equals 3.21 M. I'm going to divide by 3.21. Running out of space. So that cancels out. So my molality ends up being 0.68 is the molality of the solution of strontium chloride in the ethanol. All right, good job with chapter 9.